Good afternoon, everyone. Thanks for listening in. Today I'll have a talk on how to enhance some of the finite element results you can make within Abacus, for example, and use it for Mechatronic Design Process. My name is Jakko Nieuwenkamp, and I'm working at Reden. So I will start with a quick introduction of my company. Then I will tell something about digital twins and how finite element analysis can be useful for them, and more specific in the mechatronic design. And the last item is a quick recap. So a quick introduction of my company. We are a consultancy company. What we are doing is we are helping our clients with their optimization or design of their products or processes. And what we really try to do is to translate the physics-based models we make into knowledge, such that they can understand what's going on in their product and optimize them. I've got a few examples to show what kind of models we are making. That's on the next slide. So, for example, what we see over here is a catheter running over a track, and we can monitor what the force is as a function of the time and how this force is depending on material properties. Another simulation is an inkjet droplet. Give a pulse to the ink, and then the droplet comes out. Last example is a steel cable being pulled, and we can analyze how it feels in time. Okay, that was a quick introduction on the company. We'll now start with the actual presentation. First of all, I'd like to talk a little bit about digital twins. Not about the twin of Schwarzenegger, actually, more about digital twins, which are helping us to make decisions for real-life problems. For example, if you would have a digital twin of a bridge, and you would monitor in real life the amount of car or truck movements on that bridge, you could calculate within your digital twin what the stresses are in the bridge deck, for example, and determine when fatigue limits are there, and you need to do some maintenance, for example. So then, if we talk about digital twins, many people refer to neural networks and big data. But actually, there are not that many applications where big data is available, especially when you start a design, there's no data available at all. And in other cases, acquiring big data is very difficult. For example, if you are looking at the remaining lifetime of a product, it's not that easy to measure, and if you measure it, it will take up a lot of time and a lot of effort to gather these data points. So in many cases, we are talking about small data problems, and in these cases, modeling plays a very important role. So you can do a physics-based model, and then the next step would be to do some model order reduction. So make sure that the results which comes out of the, let's say, finite element model can be calculated really quickly. And in that sense, if you are able to predict something accurate and fast, you can use that data to learn your neural network or whatever you are using for your digital twin. And actually, that's the focus I would like to talk about today. That's also something what we as a consultancy company can deliver to our clients. So this part of the work. Now, let me focus on the mechatronic design and the use of a digital twin within such a design. There are actually there are more opportunities in this mechatronic design. Let's first have a look at the figure to the right. What we see here is a typical V model. It's the model which is being used for the design process, starting at creating some sort of a system architecture or the concepts. In that part of the design, model in the loop simulations or tests are very common, and you would like to have these tests available, being accurate and very fast, such that the control specialist can check his control strategy fast and find out how robust, for example, his control strategy is. Another way is to use that same model order reduction technique in the control strategy. So you could, for example, implement that in a feed-forward loop and use the prediction of your model to steer your actual plant, giving it a very fast response, very fast and accurate response. So what are the possibilities for model order reduction within Abacus? I've seen a presentation around 2 o'clock of one of the other speakers, and he was actually explaining already what the possibilities are within Abacus. I will not repeat that in too much detail. The general idea is that another base is being formed, a base with a lower order, so less degrees of freedom, to say it. Within Abacus, you've got the possibility to do eigenvalue extraction and complex eigenvalue extraction, and then at the end, use that data for model analysis. However, what is not possible as standard functionality within Abacus is to select the modes in a kind of automatic or optimal way. So you extract all eigenmodes, but you will only need a few of them to mimic your system. And for a simple system, it's quite easy to find the correct modes, so the most relevant modes. But when your system becomes large or multiple inputs, multiple outputs, it's not that easy, and there's no functionality for that. Another thing which is missing is the possibility to export your reduced model, and especially in a standardized way. So what we really would like is to, when we make this reduced order model, to export it, for example, in a state space form or in another standardized form, such that our clients can use it platform independent. That's what we really would like, and therefore we started a project. It's an Excel undertaking. The project is called IMEC. It has finished last year, and together with the University of Bohemia, we made this example problem. It's not being used for any specific thing. The only thing is that we can use it to find out the way we reduce the model. So here you can see that it's a mass at the end of a flexible arm, and a moment is applied on the shaft, and then what you would like to know is how much the mass is displacing based on that motor torque. So the first thing we did is extracted the eigenmodes of that system, and then using those eigenmodes, you can create this transfer function, and the transfer function gives you a very good characteristic of your system, and you can actually see how well your reduced model with only 50 modes mimics the full model, the full direct integration model. So the blue dots are the direct integration results, and the orange line is based on only 50 nodes, giving a reduction of about 600 times to the full model. So then the next step would be to find these most relevant modes to be using. We were now still using 50, perhaps it can be even less, or you want to know which modes to use. And that's based on the nodes you would like to use as input and the nodes which you would like to use as an output. Creating or finding out which modes to be used is done using balanced truncation, and the graph we see in the right is a figure called Hankel singularity values. And what this figure does, it shows you how accurate your model is as a function of the number of modes taken into account. And you can see that, for example, if you have one mode, then if you go to 2 modes, there's quite a big increase. Then if you go to mode 3, again, it's quite a big increase. And it's stable again a little bit, and then increase again. And in this sense, you can find out, okay, I'd like my model to be this and this accurate, then I will need, let's say, 10 modes. So it really gives you a very fast way to get insight in which modes to be to use. So this was the theory. What we did is we've implemented that into an automated workflow within Abacus. So first of all, it's the finite element analysis you need to do in Abacus. Then the extraction of eigenmodes, and they can be complex actually. And then the model order reduction, and the selection of the modes is being done in a GUI we developed. So it's a plugin within Abacus, and you can very easily use that plugin to select the modes using that Hankel plots, for example. And then you can select them and create your reduced order model. And then we've got 2 options to export that model. First of all, as mentioned before, it's in the state space form. Just some text files with the A, B, and C and D matrices. And then we've also got the opportunity, the option to export it as an FMU. And FMU is something similar as, for example, a step file when you concerning a 3D geometry. Only in FMU is a standardized method to export a model, and it's open source. So that means that it can be used within many platforms. It's quite widely spread. And for us, this is a very good and easy method to create these reduced order models for our clients, such that they can easily use it. It's like a plug and play option. So a quick recap. We've automated the generation of these reduced order models, and then also automated the selection of the modes using balanced truncation. Then we can export it to a platform independent standards using the FMI standards. And this method is not only applicable for linear structural dynamics, but also, for example, coupled structural acoustics or a system with systems with non-proportional damping, and then you're getting into the complex mode shapes. All of this is supported within the automated workflow we've developed. There's more to it than just linear structural dynamics. You can also use this method, for example, for linear systems, but at temperature-based or heat exchange systems. You will need a different kind of model order reduction, but it's very well possible. And then we are actually also working on systems which include nonlinear behavior. In those cases, the model order reduction is a bit more complex, but very well possible. And it's something which is being done quite a lot in the academic world nowadays. So thank you very much for your attention. If there are any questions, please ask them on the site and I'll be happy to answer them. Thank you.